Now, rather than having to put your spherical harmonics together from scratch from that equation, most times you're going to be just fine looking them up in a table. So this table is actually from Atkins, but Macquarie will have a similar one. Okay, so you'll just identify what state you're in for your particular situation. So identify your L and your M sub L, or I'll make that note here. So that would be J or M sub J. Okay, so right now we have only used the notation of M. Okay, down the road we're going to see that M value. Remember, that's going to be our magnetic quantum number when we get to the hydrogen atom. Those we've already seen depend on the value of J or the value of L. So that's why it's getting that little extra notation in the subscript there. Okay, so you just identify what states you're in. Okay, and then you'll have your form of your spherical harmonic. Okay, so when you're doing homework problems, you are, unless it asks you to specifically put together the wave function, you can just grab them from a table like this. Okay, and now that we have derived our full wave function expression for the spherical harmonics, we can take a closer look at those. So remember that our spherical harmonics are eigenfunctions of a Hermitian operator. Okay, remember we just basically obtained them through our Schrodinger equation with our Hamiltonian. Okay, so because of that, we know they must form an orthonormal set. So let's take a moment to put together our orthonormality condition for the spherical harmonics. So remember, we have now, with the full spherical harmonic wave function, we have a dependence on two variables, our theta and phi. So we're going to be integrating over both of those. Okay, so we have, let's start with our phi integral. So that has limits of 0 to 2 pi. And we'll put our d phi. And I'm going to write this one with all of the differential volume elements out front. Like I mentioned, was another convention, just so you can see it that way. And why it's kind of nice to do that when you're doing multiple integrals. Okay, so there's the d phi part. Remember, the differential volume element for phi is just d phi. Okay, that one's nice and simple. And then we have our our theta integral, which is over the limits of 0 to pi. All right, and remember our differential volume element for theta is d theta sine theta. Okay, so now we have all of our integral limits and differential volume elements out front. Okay, and then we'll just plug in the wave function expression after that. Okay, so this is just another sort of convention for writing out these integrals. You can pick whatever makes you happy. So we'll put in our spherical harmonic function of theta and phi. And that's our star, our complex conjugate. Okay, and then we get our second function here. Okay, so one thing to remember with our orthonormality condition, remember our indices that we're using for this function are not necessarily going to be equal to the indices we use for this function. Okay, so since we have a couple of different indices that we have to work with, we just add a little notation on here to distinguish them. Just becomes ever so slightly more complicated than what we were working with for the one-dimensional cases. Okay, and in the cases where we had one index that we were worrying about, where it was just an n or kind of value. So we just put a little prime on that second term. Okay, so we have J and J prime are our two options, and M prime are our two options for that. Okay, and then to finalize our orthonormality condition, we use our Kronecker delta once again. So we're going to have two of them because we have two indices that we are worrying about here, our J and our M. So we'll have one for the J's. So we'll say J prime, and then we'll have another one for the M's. So M and M prime. Okay, so essentially we've got two kind of independent orthonormality conditions that we have to consider here. Okay, so one is with the J's. So if the J's are equivalent in these two functions, then that Kronecker delta will go to 1. If they are not the same, okay, then that will go to 0, just like we had before. And same with the M option. So if these are the same, this guy will go to 1. If they are different, it will go to 0. Okay, so turns out, so since these are multiplied together, if one of those goes to 0, then your whole function goes to 0. So they have to both be exactly the same in order to have that normalization condition. And the last thing that I'll mention about these wave functions and our use of them in these calculations is that we want to remember that these are complex functions. Okay, so if we go back and look, right, some of them are complex and some of them are not. But just be careful because you are going to have some situations where that complex conjugate is going to be relevant. Okay, so we want to pay attention to this. I'll make a little note here. So relevant here for spherical harmonics. Okay, so don't forget that. You will, if you ever find yourself running into a situation where you're like, I just can't get this integral to work, I know it should come out to 0 or 1 and it just looks awful, go double check that you've put in your complex conjugate, because chances are, if you forgot that, you're going to have a mess in front of you. Okay, so that's one easy check. And then just to kind of finish this up and make our complete picture, so we now have our full spherical harmonic wave functions. We see that we can normalize them. We have this orthonormality condition. Let's just finish it up with our final expression of our Schrodinger equation when all is said and done. So now we know that our spherical harmonics are dependent on L. No, I did it again. J or L and M. They are functions of theta and phi. Okay, and we've already obtained our energy levels on our way through solving the Schrodinger equation, as we saw earlier, so we can put in our actual value for the energies here. And our wave function again. All right, so this is kind of our final official Schrodinger equation for the rigid rotor. Okay, so this is just a more specific version of our H psi E psi expression, okay, where we've plugged in our spherical harmonics for the wave function, and we have our actual values for the energy there. Okay. And last but not least, a really fun part of the spherical harmonics is that when you plot them, they make some really familiar pictures for us. So hopefully these 3D polar plots of the spherical harmonic wave functions look familiar to you. Okay, these are essentially how we get those pictures of our atomic orbitals that you know and love from general chemistry. Okay, so we'll spend some more time with those down the road when we get into our hydrogen atom. But for now, we'll just point out that it is in fact the spherical harmonics that are the angular part of our atomic wave functions. We're going to have a radial part that we add in later, okay? But this is where these familiar shapes that you know of your orbitals are coming from. It's coming from those spherical harmonic wave functions.